Welcome everyone for the final session of the academic summit. We have 5 talks in this session, all on AI systems optimization, and we will start with Professor Aditya Desai. He recently joined as a faculty at CSE Department IIT Bombay. Before this, he was a postdoc at the Sky Lab at UC Berkeley. He did his PhD at Rice University and undergrad from IIT Kanpur. So happy to have you.
Am I audible? I think it's working. Okay. So inference time context sparsity, is it an illusion or an opportunity? That's kind of the topic I'm going to talk about. And it is a part of a bigger effort. There are folks from Berkeley, folks from Rice involved in this effort. So yeah, I would like to argue that long context is becoming more and more standard instead of like just being a specialized capability that was a couple of years back. I mean, we already had like very good applications of long context, such as question answering, AI interactions, long sustained AI interactions, coding copilots, etc., which were already talking about longer and longer context. And we're also moving towards this multi-agent systems, right, where agents interact with each other. And as the interactions grow, you're going to expect this to fall into the long context category. Apart from that, there's also this trend of increasing prompt lengths. So this is a snap of like people talking about how the system prompts in OpenClaw are getting to like 150K plus tokens, right? And then there's this study from Epoch AI, which, sorry for the bad picture, which basically says that the generation lengths with current models is increasing rapidly, right? Even for the same benchmarks such as math and so on. That's just the way we are training the models. So with these kind of trends, you can think about it's very likely that long context is going to be the dominant operating kind of deployment mode for LLM inference. So it's actually a very important point to think about that, whether how well are we doing on the inference kind of front for LLM, for long context LLMs. And probably unsurprisingly, the bottlenecks there are created by self-attention. So I'm not going to go into self-attention. I think everybody knows what self-attention is. And there's order n square compute involved when you're looking at in context length. There's order n memory kind of reading and writing for the KV cache, right? There are two distinct workloads here. One is the prefill and the decode. The prefill is when the model looks at a context for the first time, which is supposed to fill all of these KV caches. So it's order n square compute, and largely it is compute bound on GPUs. Decode, on the other hand, is this autoregressive step where you create next token and you keep creating it based on the existing KV cache. So you have to read the entire KV cache and do order n kind of computation. So it is it is largely decode bound. Memory bound in this case. So now the question that we want to ask is, are these costs or bottlenecks that are created by self-attention, are they fundamental or not? And this has been a question of interest for, I would say, more than half a decade at this point. Like people have tried to do like investigations in multiple dimensions. So the first kind of approach that people have taken is maybe we can replace self-attention altogether, right? And here people have tried to explore things like linear attention, state-based models, the variants like Mamba and so on. But what is interesting to observe is the frontier models which try to take these new approaches and try to integrate it with their own models, they end up having to retain some full self-attention layers. And what it means is that there's some expressive power that self-attention brings to the table, which these alternatives have not been able to capture, right? So can we really replace them? We don't know the answer to that question. A second approach, which is spearheaded by DeepSeek, is what if we keep all the attention layers, but we make them sparse, and we bake that sparsity inside the training itself. Now, this has been very encouraging, at least for me, but the evidence that we have is still inconclusive. So the results that we have seen from DeepSeek or like following up from like ZAI is that it has only been shown to work in extremely large models. So their models are like some 500, 600 billion parameters. And with large models come more layers, more attention heads. So it is quite possible, I mean, you can be suspicious about it, that the added number of layers, added number of attention heads might be compensating for the handicap that sparsity might be inducing. So again, like, can sparse attention directly replace a full attention? We don't know the answer to that question. And the third kind of line of investigation is maybe we don't need to bake in the sparsity. Maybe the pre-trained models, because we are trained with softmax attention, they are already sparse. And if that is the case, maybe we can do inference time sparse attention. And in this case, there have been like maybe 30 plus kind of different methods that are proposed, right? But interestingly, none of them have found adoption in the state-of-the-art inference engines. And that says something, right? There's a gap between all the research that is happening and the adoption, which says we don't really understand if the value that these sparse attention bring, is it real? Does it work on the real workloads? I think all of these are open questions at this point. So this is my position on this. So I'm going to say that sparsity is the answer. You need to be sparse in the context dimension. And to kind of convince you of this, I'm going to talk about three things. So one is that sparsity is already emergent in state-of-the-art models, right? So I'm going to kind of advocate for that the inference time sparsity is a real thing. And of course, if you take it to training, it's going to get even better. The second is we can actually exploit this sparsity on current hardware, even the inference time sparsity, at least for some settings. And the third thing is people generally have been, as a community, we have been chasing some paradigms such as top case sparsity. We'll talk about it. That actually need to change. We need to evolve from top case sparsity to something like even bigger, which is where I will talk about a little bit about V-attention. So before I go into it, so let's start investigating sparsity, right, in context dimension. So I'm going to restrict myself for this investigation to inference time decode context sparsity. So prefill will happen with the standard flash attention exact KV caches. But when you start doing decoding, at that time, I'm going to apply sparsity on the context. Now, the question then becomes what kind of tokens do you choose, right? If any sort of random sparsity is not going to work. And especially this is very important in the inference time sparsity because you have to be very close to what the full attention computation is when you're doing like some sort of approximation inference time. So largely the community is guided by this kind of an understanding of a lemma where the contribution that each token makes to the output of attention is proportional to its attention score and the norm of the value vector. And largely empirically, people have found that value vectors the norms don't change too much across tokens. So that leads to an important simplification that you can actually just look at the attention scores, which in turn means that you can just look at the inner products, right? So if that is the case, then the framework for top case sparsity is actually, yes. Magnitude, the norms of the value vectors, I mean, I'm pretty sure these are very anecdotal observations. I mean, you should always have some sort of flavor to it, but actually without assuming something on the value vector, you cannot go to the inner products, which is like much simpler objective. The framework for sparse attention is quite easy. You basically you somehow have some scoring function which will score all the different key value pairs, and then you select top k from it, and then you do a sparse attention. That's what you do. If you use the exact inner product, you kind of get an exact top k sparse attention, or let's call it oracle top k. And of course, we know that if you were to do that, then you would have to read the entire KV cache anyway, so kind of defeats the purpose of sparsity to begin with. So then most of the research is just around how do you still do this? I mean, it kind of is a maximum search product problem then, right? And how do you do it through some sort of approximate solutions? That is more or less what the game is in this sparse attention reach, right? And this is like 40 odd papers that I just collected from 24 to 25. There are more before it, there have been more after it. So if you look at the research output, there's a lot of research happening in this area, but not really getting to any adoption. So what we are going to do is this. So I want to convince you that sparsity does exist in the context dimension. So I'm going to create a wide empirical study. So for this study, I'm going to stick with oracle top key attention. And the reason is that oracle top key gives me the best chance to expose sparsity if it exists. I don't want to be bound by these approximations or some approximation errors that these methods kind of introduce, and we don't really know which is the best method. Like it's a different kind of a problem to know what the best is there. So in this case, we're going to study more than 20 models spanning 5 families, different range of parameters going from 1B to 72B. It has some of the hybrid models, some of the standard models, and we're going to test it on 4 different benchmarks. So each of these, like at least Ruler, Loft, have multiple sub data sets measuring different capabilities and so on. So Ruler, we are going to select a hard subset of it because a lot of Ruler is actually saturated. But basically, the idea is that you want to do a normal retrieval multi-hop reasoning kind of analysis, which is long context. You also want to go into long generation, which is AMI. And then SWE basically is the agentic workload, which I believe is a good enough measure of whether there is value in sparsity in the real use cases. I'll go over some of the results here. So basically, this is showing you the results on Ruler hard data set on different parameter sizes, different families. So the first observation I want you to look at is the hybrid families. By the way, this is 50x sparsity. So we are only looking at 2% of the tokens in the context, right? And the hybrid families are very robust to sparsity across the different model scales. In fact, if you look at the figure on the right, we go to extreme sparsity. If you only use something like 4 or 16 tokens, for the larger models, you're able to achieve parity with the dense model. So that's how robust hybrid models are to sparsity. And the second observation, is that it doesn't really show up in the standard families, right? So which are using the standard attention across all layers. That's not the case. But interestingly there, as the model size increases, the gap actually reduces. And that you can find even like when you go to extreme, you can find similar kind of observations in hybrid families as well. Yes.
You are still doing full attention, and then you are seeing where I can do sparsity or
No. So basically, I'm doing an oracle top key attention. So the top key computation is exact, but the computation is sparse.
I still don't get it. So you do.
So there are two things in sparse attention. One is the indexer, which will give you the index, what tokens to look at. The second is sparse attention computation. You only use that tokens to kind of derive the attention output. The second step is sparse. The first step is how do you choose the tokens? How do you choose the tokens? Essentially, as I mentioned, like people generally chase this paradigm of top K. You want to choose the tokens with most contribution. That is tied up to the inner products K dot Q. So we look at the K dot Q, order it, and choose it. Now that is not feasible, is what I was saying, and that's why like generally people want to do approximations of inner products. So it's not full attention; it's a full K dot Q product, and then choose it. Yeah, I mean again, this is just in papers we can find more things about approximate. How do you do that? Yeah. So this is basically we have 64 like sync plus local tokens, right? And in between we are only retrieving 1, 4, 16, 64, 128 tokens on 64 on 32K context length. So this is like much beyond the 50x sparsity. It's like much more sparse. Then we look at like what happens when you go from 32K to 128K. So for that we use the loft benchmark. And loft is a little bit more noisy. It's a little bit harder than like ruler. So even the base models are not performing that well. So there'll be a lot of noise. But interestingly, if you go to the large models in all the model families, you will see that we are achieving dense parity with 50x. Right? Now these two benchmarks were more, I would say, long context and short generation. And so it's actually important to look at long form generation because that is the real application. And you would expect this to be harder, right? Because when you induce these when you induce errors while doing sparse attention, you're actually messing with the embeddings, right? And as you go in the generations, these errors, you expect them to propagate. So we tested one of the Quinn models on AMI 2025, and we see that like even if you go to 50x compression, it's actually able to achieve the same quality of the model. And more importantly, if you look at the amount of tokens that are generated per problem, they do show a slight increase when you go to like 50x sparsity, but the increase is not that high. What it means is we are not really trading like latency in like decode step with more generations, which is again like something that can happen. But this means that if you're able to leverage the sparsity to get gains, then you can actually get faster time to complete like task completion times. Then we apply it in a subset of Sweet, which is the Django subset. And here actually you can see there is a small drop. So we go from 71 resolved to like 67.1 resolved. So there's a small drop, but I think the absolute numbers are still pretty strong for like a 50x sparsity kind of experiment, right? And again, you can look at the mean turns per task. They show similar things, and then prompt tokens per generation per call is still not very high. Yes.
In the previous slide, is there any reason that you see a drop at 20 and back to 90 at 50? Is that like just noise?
This drop and back.
Yeah.
What is the drop?
So you see 86, 86, 90, 86.
I mean, I think these are like 30 samples. So don't read too much into like these. As long as it's like dense parity, I think it's fine. So by this point, I'm expecting like basically we covered long context and each of the benchmarks has multiple data sets. Then we went to like long generation. We also covered some of the agentic. So I hope you're convinced that more or less sparsity does exist in context dimension and it has real value for real workloads. Right? Now, the second question is, can we actually exploit this sparsity? And because I said, like when you do sparsity at inference time, it is actually very essential that you stay close to the true computation, right? Yes.
Summary, can we say Oracle Top K works very well with like even extreme sparsity?
Yes, I mean, Oracle Top K works very well, but my point is there is sparsity. Now, the gap between like approximate methods and Oracle Top K, I think is not that big. Like you can use methods like PQ cache and they work really well for real workloads. And you can check out the skylights, like actually where we do this kind of experiments. So I believe there's like not just for Oracle, but I feel like, I mean, Oracle is what we can draw from this, but I feel like even practical methods are actually very close to that. Yeah, so I was talking about like whether can we leverage this sparsity on the hardware, right? So in case of inference time sparsity, we have to do a per query per head dynamic sparsity if you want to stay true to the underlying computation, right? And so this is basically a lot of times when I talk about sparsity, people give me looks that you cannot really leverage this sparsity on the hardware. So that's not true, right? In decode steps, so we basically took a flash infer kernel, we modified it with the sparse, like to make it into a sparse kind of backend. And if you just use the sparse backend at 50x sparsity, which is what we have been talking about through the talk, you can get up to 10x speedups in the backend kernel itself, right? And with training, if you can go beyond the sparsity, there are actually much more gains to be made. Now, again, the previous slide did not include some sort of indexer cost. So we took like one of the practical indexers, which is double sparsity in this case. We used a relatively conservative kind of a cache for it. So double sparsity uses this metadata cache, let's call it whatever you want to call it, label cache, right? And so it has like, let's say if you use 128-bit cache, which means that for every token, it has to read 128 bits to do the computation of top k. Then still at 50x, we're able to get decent kind of improvements on the total kernel. So this is completely replacing the flash attention kernel or flash infer kernel in the backend.
Is the approximation scheme there? How do you figure out which top K?
So double sparsity is basically they do some sort of AWQ to identify channels which are like outlier channels or like important channels, and then they reduce from the like 128 dimensions to like 16 dimensions or so. Yeah, but like in this case, I did not use like a very good version of double sparsity. You can go like you can do like a quantization on the top of label cache and like till 4 bits, it seems to works pretty well. So and these are like I would say lower bounds of what you can get, right, in terms of speed up. So there's like this is the lower bound, the previous slide is the upper bound, and somewhere in the middle lies the true gains. And by the way, I just want to mention like previous slide, this was actually on GQA, right? So GQA number of query heads are like a factor above number of KV heads, right? And if you are doing a per query per head sparsity, you can argue that this is not a good idea, but that's not true. Like there's still gains to be made here. Okay, so I have some time. So last thing that I want to say is, so we have seen that there does exist sparsity. Sparsity can be leveraged. Now the question is, what is the nature of the sparsity, which is the true nature, right? So in our experiments, we saw that there was a gap in the standard families, and the gap was significant and consistent. It seems like a statistical thing, right? It is there. And we also saw that SWE benchmark is basically one of the hardest benchmarks that we have tried. There is small gaps. So the question then becomes, does top K always work, right? And we tried Oracle top K. So anything that generally you would propose is basically upper bounded by that lower bounded by the performance. So there's a reason why top K does not always work. And the premise behind top K is that the attention distribution is inherently low entropy, which means that only few tokens contribute the most to attention output, right? And if that happens, then yes, top K will give you the lowest errors, but that does not happen in practice. When these models are trained, there's no sort of incentive for it to do that. So oftentimes you'll find that across different heads for different queries, the distributions actually vary a lot. And so in that case, you'll find these. So in this case, this is like on the x-axis, you have sorted tokens in some sense, or sorted by in descending order of the attention scores. And we are basically looking at the cumulative attention score, right? So this is like showing how much of coverage, quote unquote, you get when you sample, when you pick the top K tokens. So if you have something like a red line, the top K is going to give you a very big error, right? So you kind of expect that top K will fail in these kind of cases. And general kind of counter method that people have proposed is to do top P, which says that basically if the attention scores are diffused, maybe you need to look at more tokens. But if you do that, you basically get rid of the sparsity. So then the argument that sparsity does exist actually kind of fails, right? So we argue that that's actually not the right way to look at sparsity. So,
Question. So
yes.
why is that? I mean, it can be very dependent on the particular input, right?
yeah,
That in some cases, like let's say 90% are sparse, but there may be like or 2-3% cases where you need top P or some layers in some input need a top P.
yeah.
So you're still sparse 98% of the time, but 2% of the time you do this and you don't lose accuracy, right? So
Right.
it seemed like a good trade-off to me.
Depends on how much top P you have to do. I think that is I mean, somebody needs to do that study. And also top P is very hard to estimate. So top K approximation is still easy. Top P is going to be, I mean, I have seen 3-4 papers on it, and I don't think they are good. Like, I mean, the kind of proposals they have made are not really like very good. But apart from that, I think it's more of a philosophical question whether sparse attention, I mean, does the attention on long context should that be dense or sparse? I think it's more philosophical, more. And actually, there's theories that we can look at where, I mean, actually, we have some arguments made in our own papers where we say that on the long context, dense attention does not mean much. You need to have sparse attention to really capture the long context. So there are arguments around that as well. So I think when I say that top P is not the right thing, I think it comes from more of a philosophical back end that attention has to be sparse in long context. So yeah, so the idea is that we propose this fancy symbol attention, which I'm going to call as V attention. And I feel like Microsoft folks might get offended at it, but I think I'm going to just do that anyway for this talk. So the idea here is that what do we do, right? How do we take care of these diffuse attention distributions, right? So the idea is in the extreme kind of situation where the attention scores are very diffused, instead of doing top K, there's actually a better method that you can just sample and estimate the attention. Because diffuse scores essentially means that there's a very small variance in the attention values, right? So sampling is actually a much better sample efficient method to do that. So in V attention, what we do is we break down this task of attention approximation into two parts. One is the top K component, and then whatever the residual is which top K leaves behind, you approximate it with random sampling, right? And there are more interesting discussions that are in the paper that you can look at. But just one thing I want to highlight is because we are using random sampling, right? We kind of have a good understanding of how good or bad this estimation is. And if we know that, then we can actually decide how much sample size we should take to ensure some sort of error guarantees. So as a user, you can tell me this is how good an approximation you want in terms of the epsilon delta standard probabilistic guarantee, and I'll try to achieve that using my budget computation. Yes. Random samples or budgets? What? Sorry.
For the random, the ones that you pick at random, you pick the values along with the attention rate.
The V values.
Are you talking about the budget or are you talking about when you say values, what do you mean? The V.
The KB.
The V of the KB.
Sorry, can you repeat the question? Maybe I'm not getting it.
So when you're saying you use a random sample to approximate what is the residual
Yes.
attention weight, right?
Yeah.
But then how do we use that for figuring out which values and which values are to attend to?
That is the randomness part, right? So if you have some range in which you want to sample, you just do a random sample on the index, and then you pick the values. So random sample is not randomly creating values and keys. It's randomly choosing the index, which
Then
tokens
you
to
might
pick.
as well use a random value, right? Because it's
No,
random.
No. I mean, random values will give you a random distribution, like sample from a random distribution. You still need to be true to, like, if you want any sort of guarantees, you need to be true to the actual distribution of Ks and Vs, right? You cannot move away from that distribution. Like random sample is going to just help you estimate that distribution.
So what is the intuition here that if after top K, the remaining distribution is more or less uniform? Is that the intuition?
Yeah, kind of. I mean, it need not be uniform. So we'll estimate the variance and we'll compute the distribution and stuff. But the idea is that there's this top K part, and then the rest of the part is kind of more or less uniform. More or less uniform meaning that the variance is low. And if the variance is low, you can approximate it with a small enough sample size. Yes.
So you're also evaluating on JAMA models. So
Yeah.
I just wanted to, I was curious, like, how are you doing top K there? Because there are like sliding window layers in between.
Yeah. So that's the hybrid nature. So hybrid layers are already like very low on memory.
Right.
So you don't need to sparsify those.
Okay,
So we
only
start
the-
with the full attention layers.
Okay.
And even there, because their contribution to the overall latency is very small.
Okay.
So real bottleneck still lies in the self-attention layers. And that's what I was trying to say, right?
Mhm.
You want to replace this, but I think I'm over time. You want to replace this, but you're not able to replace all the attention layers. So bottleneck still remains.
Got it.
Yeah. So if you do V attention, you can see that even on the smaller model sizes and like standard families, you are able to recover most of the quality, right? And that basically kind of covers what I wanted to tell you today. There's context, sparsity and context dimension. It can be extreme. Already exists at inference time. If you do training, probably it's going to be better. You can actually exploit the sparsity on the current hardware. And if you do training, you can make it a little bit more regular for you to do more things with it. And thirdly, we have to shift away from chasing this paradigm of Oracle top key and probably go towards better formulations of sparsity to really unlock the gains that you can achieve. Yeah, so that's kind of it. This is again like part of a bigger project, and there's the website and all the links and stuff. Yeah, sorry. I'm sorry for going
Maybe
over time. Yeah.
we can take maybe one more question.
So one thing we found is in that some of these models, it's the initial layers which show less sparsity.
Yeah.
Did you try experiments where we just control for those layers, like let dense attention happen in those layers?
So generally, like till Quest, I mean, when Quest came out, I think a lot of those methods were doing this initial layer thing, which I think is a good idea practically. But again, when I'm looking at it from a research perspective, I don't really want to do that, because my whole philosophy comes from the fact that you should not be doing dense attention on long context. So I think like, so in these experiments, we kind of stick to, and there's like a section in the V attention paper, I think, where we talk like in detail about like what is the evaluation kind of done, like how do we do the evaluation of sparse attention? Because we read like, so like many papers are just doing their own ad hoc things. I mean, so for example, Magic Pick does this weird like 0-16 being dense, a Quest does like first 2 layers being dense, and then in the evaluation, they don't really apply sparse attention on the question part, they apply it only on the generation part. And then like, there's so many weird things that happen. It gets very hard to compare against these different methods. But I feel like I mean, if you really kind of want to look at this question of whether a bottleneck is fundamental or not, I think you should be doing sparse attention in everything. Yeah,
So with that, let's
thank you
thank
so much.
Aditya. Next, we have Sanchari Sen. She's a faculty at PSA department at IISc. She works on hardware software co-design for efficient AI systems, including domain-specific accelerators and compiler designs. She received her PhD from Purdue and BTech from IIT Kharagpur. She has received several awards and made contributions to IBM's Spire AI accelerator that is integrated into IBM Z17 and Power 11 systems. With that, looking forward to your talk.
Hi, everyone. I'm audible. Okay, so today I'm going to talk about some broad set of like cross-stack approaches for building efficient AI systems. Before I go into the details, I'll just motivate the overall idea a little bit better by highlighting the cost of AI. I'm sure most of you are aware of this, but I'll just give some context here. So the first cost that I'm going to talk about is in the context of compute, where, it took a little bit of a time. Yes, sure. So in the context of compute, so the graph here has different models, different deep learning models, with the x-axis showing years and the y-axis quantifying the compute cost of them in terms of the training flops or floating point operations per second. And the key trend here is how the cost has increased 32x every 2 years, which is well beyond what we can get through Moore's law, which is, I mean, 2x almost every 2 years. So the next is the memory cost. Again, the x-axis is showing the years timeline, y-axis is really model parameters, and the graph here is showing how the model parameters have gone significantly higher, more than what can be provided by the underlying hardware system. So the yellow is really the memory provided on the different GPU platforms, and the purple line is really the overall memory demanded by these different AI models over the years. And all of this adds up to also increase the energy cost of the AI models. And the number that I have here is from ChatGPT last year, but things have increased significantly over what I have here. This is from last year, where it says that if we look at all of the ChatGPT queries across all of the users per year, it amounted to about 310 gigawatts hours, which is equivalent to powering about 30,000 US homes. So the point that I want to make here is that we need to address these high compute, memory, and energy requirements of AI models for enabling more scalable AI execution. Yeah, I mean, the good news here is that there are some characteristics of the AI models that can be exploited to address these high compute, memory, and energy demands. And the first characteristic here is the fact that these are composed of a finite set of layers and operations, like some combination of convolution, fully connected, ReLU activation, JeLU activation, batch normalization, pooling, etc. The other characteristic is this fact that there is some kind of an error resiliency inherent in these models, wherein even if you perform some of the computations in an approximate or incorrect manner, you'll still be able to get the correct output. And the example that I have here is in the context of say a classification network, where you are trying to classify between a cat and a dog, and the final probabilities will tell us whether it's a cat or a dog. And what you really care about is the final winning probability. You often do not care about the exact value of it. So even if there are some errors in the intermediate computations, you might still get the cat to be your winning probability. So this is kind of something that we can exploit in the context of these AI models. The third characteristic is often this static nature of operations here. So irrespective of whether you are operating on the image of a horse or an image of a dog, you will be executing the same set of operations on them. And this is true even in the context of, say, mixture of experts, where the exact fully connected layer that you are running is different, but the computations that you do will be the same. I mean, it's just the model weights that you're loading are different. The final characteristic that I want to highlight is the presence of sparsity. We did learn a lot about it in the context of KV cache or attention in the previous talk, but I also want to talk about it more broadly, where even say in the presence of layers like ReLU, you will introduce sparse activations, and then through techniques like pruning applied on the model weights, we can end up getting sparse weight values that are present in them. And there have been a wide range of techniques that have been proposed to exploit these characteristics and improve the efficiency of the AI models. And the first characteristic in the context of finite set of layers and operations has led to the development of a wide number or wide range of specialized AI hardware accelerators, starting from Google's TPU, and I also have IBM Spire highlighted here. This was something that I worked on at IBM Research, and I'll be talking about more. And of course, there's the Maya accelerator from Microsoft that was also announced very recently. Then the other aspect that I spoke about in the context of error resiliency can be broadly exploited through these approximate computing techniques for AI. And this can be some approximate operations like approximate attentions, then the use of quantized or low precision representations for the different data structures. And finally, like also the use of certain approximate compute units all the way to approximate adders and approximate multipliers, for example. The third property in the context of static nature of these operations can be exploited to come up with efficient mapping and parallelization techniques, which will tell you that, and the static nature is very important here because you can do this once offline. You know that these are the operations that we have to run, and this is the optimized way of running it. You can take all the time it takes to kind of explore that design space and come up with the most optimized mapping. And that is where the static nature is very important. And finally, in the context of sparse operations, we can exploit or sparse operands, we can exploit it in two different ways. One is through model compression, where we can store these sparse operands more efficiently in a less memory, in a smaller memory through compressed representations. And then we can also skip some multiply accumulate operations that are born out of sparsity, because these zero values make these operations redundant. And through my research, I have looked into advancing the state of the art along all four directions for improving this efficiency of AI execution. And along the first direction of specialized AI hardware accelerators, I've worked on IBM's AIU Spire accelerator. In the context of approximate computing, I have looked at applying or identifying opportunities for approximate computing, which are unique to different types of neural networks, from LSTMs, from transformers, and spiking neural networks, and so on. And then in the context of efficient mapping and parallelization techniques, I've worked on the compiler for the IBM accelerator, which I'll also talk about more. And in the context of sparsity, I've looked into different model compression and zero computation skipping in the context of general purpose processors, in the context of accelerators, and so on. And through these works, the key thing that I also want to highlight here is that through these works, we had to look at the full stack of AI systems, from the algorithms to hardware, to look into the different opportunities present in the different levels and exploit them at the right level, essentially. And to give some more flavor of the kind of work that could be done here, I'll go into the details of accelerator and compiler design for a specialized AI accelerator from IBM. Some background on AI accelerator here. Most AI models today are some form of neural networks, as every one of us know, which is really large-scale interconnected layers of neurons. And each network is composed of a fixed set of layers. It could be convolution, fully connected, ReLU, batch norm, etc. And what really differs among them is the connectivity of them and their size, or the number of such layers, right? And one of the other key observations here is the fact that the operations in each layer can also be mapped to a smaller set of primitives. So for example, convolutions and fully connected layers can be expressed as vector matrix multiplications or matrix-matrix multiplications. ReLU, batch norm, or biasad can be realized through comparison, addition, multiplication, and so on. And this makes it very ideal for hardware specialization or customization, because all you have to do is to really focus on these primitives, come up with the substrate that can do these primitives very well. And we don't have to, of course, care about any other thing that you might be doing in a general purpose processor, like browser surfing or say word editing and so on. And this has obviously been exploited in a lot of accelerators that were proposed over the years, starting from, say, something from academia like Iris from MIT, for which eventually inspired TPUs from Google. Then we know about LPU from Grok, Cerebras, and so on. I'll talk about the accelerator design for the IBM Spire accelerator in more detail. And this is consisting of it's a system on chip with 32 cores connected through a ring, bidirectional ring, and which is also connected to a main memory. And each core is essentially consisting of a pair of these systolic arrays with multiple levels of memory scratch pad, an L1 and an L0 scratch pad. The systolic arrays are the ones which are executing the fully connected and the convolutional layers. And one of the things that was very, I think, which was like present ground up in the design, is the fact that this was designed to have mixed precision processing elements to really account for the quantized representations that can be used in these AI models. So each of these processing elements actually supported multiple precisions in floating points and integer representations. And then we also had, each of these processing elements also had a local register file to store some of these the data structures locally and reuse them as much as possible. In addition to the systolic array, there was also these special function units present, which can execute the activation or the normalization or pooling layers. And if we consider mapping a basic convolution operation onto this systolic array, this is what the data flow looks like, where you would have the input and the output streaming from like input from west to east and then output from north to south, and the kernel is present locally in the register file. So this is a weight stationary data flow that is employed here, and that allows you to kind of maximally reuse the weights present here while also feeding in the right set of inputs and outputs in the process. The software stack is also very important in this context, because the success of an accelerator depends on the robustness and flexibility of the software stack that supports it, right? And this stack is designed to extract maximum performance or core utilization under a variety of constraints. And it's also designed to have the ability to easily offload from common AI frameworks like AI, PyTorch, and TensorFlow. And this had a custom compiler and a lightweight runtime associated with it. I mean, the overall framework is shown here where you could take a network specified at the, say, the PyTorch level, feed in the graph that is captured, and you perform key steps in compilation, which starts from a graph optimization step, followed by some kind of a scratchpad management and work assignment to really talk about how we divide the work across the different codes of the accelerator that I mentioned, and how do you pin the individual data structures to the scratchpad memory that's present in them. And in the process, we also have to do some kind of a design space exploration to come up with the optimized mapping there. And eventually, we have to go for the code generation where the more traditional optimizations of loop reordering, dead code elimination, common sub-expression, all of that applies here. And there's obviously some kind of a performance tuning that is involved in it to guide the overall design space exploration here. That's the overall framework that we employ, but I want to give you a little bit more flavor of some specific problem that we had to solve in the context of this accelerator and the compiler. And this work was titled DNN Dasher, which is a compiler framework for data flow compatible end-to-end acceleration on IBM AIU. And the problem that it's targeting is really this end-to-end acceleration of AI workloads. And why do I highlight this end-to-end acceleration? Because this end-to-end acceleration means that we need to map all operations of the workload to the accelerator. And it's not just the convolution and the matmul. Convolution and matmul is what is really spoken about more than some of the other operations. But the key here is that we do also have to, for example, map a data operation like reshape, which may be present, because otherwise, if we are mapping the reshape to the host, it will introduce a lot of data transfer between the host and the accelerator. So in this end-to-end context, this mapping of all of these operations is important. The other thing that we have to make sure is that we need to maintain dependency across operations, wherein the producer operation should produce the output tensor in memory in a manner that the next operation can consume, right? So for example, you have this tensor T between which is produced by the matmul and consumed by the softmax operation. We have to make sure that the previous operation is producing it in a manner that the next operation can directly consume it in the accelerator. And the key to performance in such an end-to-end acceleration setting is to reduce any overheads that can be introduced by the above. And we do, in fact, observe that there is a significant overhead that comes up in this end-to-end execution because of data shuffles. And what do I mean by data shuffle? Data shuffle refers to reorganization or redistribution of data across the memory units that you have in the accelerator. And there are two different sources of this data shuffle. One is the presence of data operation, which could be this reshape or transpose or concat or slice, things like that that is often introduced into the model definition. And the other source is the use of different data flows across the producer and consumer operation. And there's one example shown here. So you would typically take a tensor, say a 3D tensor of this form shown here, and you would place its elements in some form in memory, organizing it into first something called a data stick. And the data stick is what you will say feed to your systolic array continuously in a contiguous manner, right? But what happens is the next operation is somehow demanding that its data stick is along a different dimension. It has to consume the data elements in a different manner. And the moment that happens, you need to introduce a data shuffle to go from a data stick organized along D3 dimension to data stick organized along D2 dimension, for example. And we do see it in action in a lot of scenarios. say, for example, in the attention context, where you have to go from, say, the QKV tensors to a K transpose tensor, which gets consumed. And also in the context of training, where you would often have to do weight transposes in your overall back propagation. So because of these transposes and how you're consuming these tensors, we often have to do these data shuffles. And we observe that this account for a significant overhead during end-to-end of execution, almost 60%. And remember, this is after the individual compute operations have already been optimized. Like you have made sure that you're using the systolic array maximally when doing the matrix multiplication or when doing the softmax. When you have taken the maximum performance for each of these compute operations, these data shuffles start to dominate, and you have to do something about them. And what we do here is to really come up with techniques to reduce overheads from data shuffles. And some of the techniques that we employ are, the anywhere padding, then intra-data stick shuffle with systolic array, and the use of virtual tensors. I won't have time to go over all of them today. I'll give you the details of one of the techniques here. But overall, the objective here is to exploit the static nature of AI workloads to identify the following during compile time. That is to identify the required data shuffles and to determine the nature of the data shuffle, whether you have to do intra-data stick, whether you have to change individual elements within the data stick or change the arrangement of data sticks across the overall tensor. And then we help reduce their overheads by reducing the number of elements shuffled, by increasing the granularity of data accesses from memory and so on. And the example technique that I'll highlight here is the use of a systolic array to do an intra-data stick shuffle. And an intra-data stick shuffle that I'll talk about here transposes the data stick dimension between two operations, which is common during both inference and fine-tuning. This is what I spoke about before. And the example here is that when you want to go from a data stick arranged along this dimension to a data stick arranged along, say, the different patterns of same color. And the basic idea here is to use the systolic array, which would typically remain idle during this data shuffle. And the overall idea is very simple. You have to load these data sticks from the west, and you need to shuffle them or flush them from north to south, and that automatically changes your data stick dimensions, and you are able to do this more efficiently compared to, say, an L-squared transfer that you had to do when you were trying to do it in an element-wise fashion instead of at a data stick granularity. So this allows you to do this much faster. And overall, we did get some measurements for speed up on the actual hardware with batch size of 1 and batch size of 4 here. And the graphs are shown here, where we show speed ups with respect to baseline of 1. And we also show 1 bar, which is corresponding to zero cost data shuffle, which is really an ideal scenario which you cannot really achieve in an actual execution, because you do have to do some of these shuffles. The objective here was to reduce the cost of them, and we do get some significant speed up both for batch size of 1 and batch size of 4. So I am out of time. I wanted to cover a little bit of sparsity computing, but I'll skip it for now, and I'll maybe go forward to maybe some of the conclusions, the conclusion slide that I had here. So 1 second, I'll just go there and we can stop. Yeah, basically, the conclusion that I had was really that we need to, in order to enable more widespread AI, we do have to address their high computational memory and energy demands. And addressing these challenges often involves looking at the entire system instead of isolated optimizations. And as part of my future work, I am interested in addressing these system design challenges for next generation of models and also next generation of hardware platforms. And by next generation of models, I mean diffusion models or some of these state space models. And by next generation hardware platforms, I mean more, say, heterogeneous computing platforms composing of CPUs, GPUs, accelerators, and so on. And I'm also interested in developing AI that can automatically apply these, come up with these system level optimizations and apply them as and when required. So thank you for your time, and I'll be happy to take any questions.
Hello. Ma'am, my question is regarding hardware optimization. So we have different approach when we are training the model and when we are focusing on the inference, or it's a common between.
So some of the things are common, some of the things are not common, I'll say. So if you look at the primitive operations that are present, it's still matrix multiplications, both during training and inference for most part. But that's the overall nature of these will change. So you will be more compute bound in the case of training because you have larger compute operations that you will be operating on. The other thing that happens is in the context of training, you often have to go multi-accelerator or multi-chip to do these large training jobs, and there communication can start to dominate a lot. So you have to also optimize for some of these communications. But yeah, I mean, there are some things which are common across inference and training, like the primitive operations, but then there are certain things which are more important during training versus in inference and versus vice versa.
So one of the things you mentioned is that these are consistently static operations where data flows, right? So does this lend itself quite well to something like an FPGA, like you see on DPUs? So that was my first question. And the other one was, is the systolic array like a good hardware design choice for training side as well? Because I think most of the implementations that I've seen on the consumer side at least are for inference only workloads like NPUs and stuff.
Okay, yeah. So regarding FPGAs, I think, I mean, the fact that it is static is what is lending itself to be very good for accelerated design, where you design it once and then you use it. And of course, then for FPGAs too, I mean, I think the advantage that FPGA brings in is the fact that if somehow you want to cater to a little bit different workload, you can reconfigure it faster than an actual accelerator. But people have found value in going for the fully specialized accelerator itself and no longer restricting themselves to FPGAs because they are stable enough for the kind of workloads we have seen so far. And regarding like inference versus training, I'll actually disagree with you on like saying that it's only for inference, because I mean, TPUs, for example, are deployed a lot for training Google workloads. So, I mean, and they do employ systolic arrays. So I would not say that that is really what systolic arrays are good at. But yes, I mean, people have, I mean, there are a lot of companies who are focusing more on inference side, and therefore they have deployed it in the context of inference. Thank you.
Yeah, you talked about approximate adders and multipliers. Nowadays, people are looking at deterministic inference. Do you think deterministic inference?
Yes, yes.
Do you think that can be done with these kind of hardware?
Yeah, I mean, that is a challenge with this kind of, I mean, using approximate adders and multipliers. Yes, it will definitely interfere with your like deterministic inference kind of objectives. But a lot of times people are okay with getting good enough results for a lower cost. I think we also choose between Claude models, and we are okay with the not so great Claude models in some sense. So it's a trade-off there.
Okay, so let's thank Sanchari again. Next, we have Abhilash from IIT Delhi. He received his PhD from Purdue University. Same as Sanchari. He works in systems broadly, including ML systems, distributed systems, operating systems, and mobile systems. He's a recipient of Google India Research Award in 22 and ACM and the Best Community Paper Award at ACM Mobicom 2022.
Thank you. Thanks for having me here. It's a privilege to talk to all of you. So I had planned a talk in distributed storage, but given the audience and the interest, I thought of switching topic to another work that we do. So this talk will not be about LLMs. So we just started LLMs in last 6 months. So we are looking at some different problems there. We'll be happy to talk offline. So this is not going to be about LLMs for now. Okay, so this talk is about ML workflows, and yeah, so we all know there's a lot of unstructured data like images, videos, conversations, and documents which were not amenable to automation, which are now have brought because of ML models. There are a lot of business use cases and law enforcement use cases that are possible to solve because of these ML models. So we call this end-to-end pipeline from data to output as an ML workflow. So for instance, you have some ID cards and you want to extract some entities out of these ID cards. So we call this as an ML workflow. And this ML workflow takes your inputs through a series of steps, which may or may not be ML models. So you may be cropping your card, then picking some channels and doing OCR, classify the card, then again run a country specific model to extract information, and finally write it to some CSV file. So because these are such pipelines, they are very well suited to work inside a data flow system like Flink or Spark or so on. So we can wrap these ML models inside these UDFs that are already supported by these systems. So we can express OCR as a map function, filter on the class predicted by the classifier, and so on. So one major problem is that the traditional data flow operators were working on very well constrained inputs, right? So if you had a tokenizer getting a string and it's outputting a list of strings, or you have a list of integers, its sum is just outputting a sum, right? So this input-output relationship was very well defined. So there can be implementation errors, but we didn't see that very often. But with ML-based operators, now what is happening is because the input domain is completely unconstrained. So just imagine OCR. It has to work on handwritten text with variable fonts, different colors. There can be background colors and so on. So what ends up happening is they end up making mistakes, right, without any warning, right? So suddenly now within your program, suddenly some guy is just randomly injecting mistakes. So the broad research agenda is like, how do you deal with this within your programming language level itself? Right. So just to carry on this example, let's say, so you have this traditional operators like channel picker intertwined with ML operators like OCR. And now if someone introduces a mistake, let's say the classifier misclassifies a document, a US card as an Indian card, you suddenly start seeing wrong outputs, right? And this affects your end-to-end accuracy. So handling these errors is crucial for developing effective ML workflows, right? And this is the goal of the system that we are building called Popper. So the idea of Popper, it's more of a programming framework and not necessarily tied to an individual model as such. So the idea is Popper lets developers specify alternates for these logical operators, right? So for OCR, you can say that I can do OCR with easy OCR or tesseract. I can pick these different channels. For the classifier, I can use top 2 classes from the classifier. So this is the first abstraction that Popper provides, that operators can specify alternates, right? And we don't care. So it can be prompts, can be different LLMs, whatever they can be. The second abstraction is you can write assertions. So for instance, in the misclassification, it's not immediately clear that a misclassification has happened. So that error becomes clear much later in the program or in the workflow. So you can write those assertions. Let's say you say that name should not be null. So these are the abstractions, and then Popper takes care of rest of the things. So when, or hopefully, so when we catch an error, the data flow sends it back. And in this case, let's say you automatically try a different different alternate in the classifier provided by the programmer. And then we efficiently propagate these changes forward in the data flow, right? So in this case, we delete the wrong class USA and add the second class India and end up getting the right output, right? So this is the abstraction that we are building, and we have implemented the Microsoft's scope language in Python from scratch. And the two main ideas are this logical operator like OCR. So it's a data flow language, like a database. So things are like tuples that are moving around, rows that are moving around. So this OCR is a processor, which is scopes map. So it takes a row, which is an image, and outputs another row, which has a column called OCR. But this column OCR can be generated from multiple functions, right? So it can be easy OCR or tesseract. And then this assertion is also a processor, just like a map. So if it doesn't like an input row, it can just say, I don't like this row, right? So it can do arbitrary checking on the row and just declaratively say, I don't like this row, right? And then the Popper runtime will try to send this row back, try different alternates, and hopefully next time you like the row. So we try, so we have built this system, and we try running 500 cards through this pipeline where we are extracting 3,400 total fields. So we noticed that if we call each of these combination a plan, so now we are using some database terminology. So if we call each of this combination a plan, we are representing that as a blue dot on this precision recall axis. The number is the F1 score. So we see that Popper is able to extract better F1 score than any of the individual plans, right? And this improvement in F1 score leads to reduction in human in the loop cost. So just with 0.04 improvement in F1 score, you could extract 120 extra cards where all the fields were extracted correctly. So this is how we are approximating. Yeah. 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 So that is a online optimizer that we are building, profile guided optimizer. So I'll talk about it. Right. So it improves precision and recall over any individual plan, reduces human in the loop cost, which in this case we are approximating as how many cards all the entities were correctly extracted. So the reason this tends to work is because these models are trained independently, right? So these different plans tend to have uncorrelated or somewhat not completely correlated failures. So for this particular example, this is like a Venn diagram. So the blue circle shows this easy OCR and all colors plan, right? So this was able to extract 83.1% fields correctly. But if you change to red color, you can get 4.7% extra fields. If you change to tesseract, then overall, this is not a very good plan, but it can still get 2.7% extra fields from the output, from the input cards. And we are also deploying this at an industry partner. So they just completed their POC where they tried it on 500 documents. And they are pretty motivated by the results. So they are going to try it over a 250,000 document use case. So there's some details from their POC. So this is not like the cards pipeline. This is a more of a long context extraction, very long documents. So there they have to chunk the documents and they put it in a vector store, then they retrieve it and finally extract it using LLMs. So there they specified some choices based on their domain. And these are slides taken from their presentation. So they observed a 19% jump in the accuracy. And the thing they especially liked was that, so 19% jump compared to any best plan, right? And the thing they liked the most was that Popper could use cheaper LLMs whenever it could, right? So you could try cheaper LLMs. When they fail assertion, then you try the more expensive LLMs. Okay, so this is just the overview. So in overview, basically ML models can make mistakes anytime. So we don't know what to do. So what we can do is probably try to write some assertions to at least know that they have made mistakes. Now, when you know they have made mistakes, what to do? So we are just asking the programmer to give us some choices. And yeah,
So did it, can you talk about like, did it actually require more time because it would kind of like trying the smaller LLM, then going back and so on? So did your throughput of processes actually decrease while potentially, and as you say, while increasing the quality?
yeah, very much so. So that's why the focus right now is not at all on real-time use cases. We are just focusing on batch processing, right? So you are a bank, you got a bunch of documents for a day, and now in the night you want to process their loan applications, right? So the turnaround time is not the most important metric. The most important metric is the human in the loop cost, which is tied to the accuracy.
Okay.
As well as the cost of LLMs, right? So you don't want to spend too much money. These are the two main metrics. Runtime is less important in this setting. That's why, otherwise it doesn't make sense, right? If you want to, if it's an interactive thing, then you cannot just keep rolling back. Any other thoughts, questions before we look a bit more detail into Popper? Okay, so let me tell you, given the time that I have, let me tell you a little bit more about the architecture of Popper. So there are two main components that we need to work on. One is the execution side of things, right? So once you catch an error, you somehow have to trace it back, right? You have to go back in time. You have to change some upstream temporary variable in some sense, or intermediate computation output. And then once you change it, you have to flow it forward efficiently, right? So these are the two goals of the execution that we have to solve. Then the other component that we have is this online optimizer, right? So there's like a profile guided optimizer. So let us say you have seen this document fly through this pipeline many times, right? And it maybe failed assertions and you had to try something else. So over time, you can learn that some particular plan seems to be working very well, right? So now that you try the next batch of inputs, you can just try that plan first, right? So just to combine these two things, this is the overall architecture. You have a query executor, you have a query optimizer. So we get an ML workflow, then we do some standard database optimizations like predicate pushdown and so on to get a logical plan shown in black. For each of these logical operators like OCR, you can have multiple choices given by the programmer. So this online query optimizer maintains certain estimates on how good a plan is. What is the probability of passing the assertion for a given plan? And it also maintains some estimates of the runtime, like, right? So, but this runtime can be swapped with cost, right? So how costly is this model? So this optimizer then gives a sequence of plans to the executor that please try this plan, then this plan, then this plan. The executor just follows this sequence. So when an input comes, it tries a particular plan. If it fails assertion, it tries the next plan in the sequence. Sorry, it tries this particular plan. When it fails, it tries the next plan in the sequence, reusing the intermediate outputs, right? You don't want to redo the whole thing. And then when this mini batch finishes, then it sends back all the observations back to the optimizer, at which point the optimizer can update its estimates to give a new sequence of plan for the next batch. Right? That's so some more details. I will not go. Okay, I think I'm doing good on time. I could have gone into more details, but Yeah, I will not go into too much details, but so the data model, so the reason we chose to use a data flow language is because these UDFs has very nice properties. And these UDFs typically do not make any side effects, right? So you're not changing the file system state, and now you have to roll back the computation. You don't have to worry about these side effects, right? So these data flow models, data flow languages have very nice properties. Right? So when you roll back, you just have to delete the rows and then propagate the deletions forward. So in the data model, what we have is we maintain a lineage. So every row, you remember which row did it affect in the future, in the next operator, and so on. Right? So we maintain both a backward lineage and a forward lineage. That just means backward pointers and forward pointers. So now when an assertion fails, we just follow the lineage back and we say, okay, I need to change this, or let's say change this to this one. And then this fails again. So then you again follow the backward lineage and say that I have to change this one to this one. And finally it passes. Right? So the data model is simply just like a database. Every operator has an output table. And within the across the tables, you're maintaining this backward and forward lineage to go back from assertion to ancestor row. And then once you're editing the ancestor row, feed the update the outputs efficiently. So the optimizer also maintains a monitoring log. So every time this operator tries a particular physical operator, it remembers how long it took for this particular input. It also remembers all the successes and failures of every plan inside a plan log. So now this log is what gets consumed by the query optimizer once this particular batch ends. Right? So this batch processed 100 documents. Now this has ended. So the optimizer will re-optimize, give you a new sequence of plans. Right? So the goal of the optimizer, so there can be many different goals, but the goal of the optimizer for now that we have set is to minimize the expected running time. Right? So what that means is you want to try the cheapest model that runs fastest and has very high probability of passing. Right? You want to try that first. If that fails, you want to try the next best model that has less runtime but still high probability of passing. Right? So it discourages very heavy models which may have very high probability of passing, but they get penalized on this runtime term. Any thoughts, questions, comments?
So this runtime cost, these are all profile based.
This is all profile based, yes. So the optimizer will learn this over time, how long it is taking to run this particular model.
It's not off. Profiling is not offline, but
Online.
while you are actually.
Yeah.
And do you actually see that the number of failures going down as over time? Because it should.
Yeah. So the question is, do we see
and the cost should go down too?
Yeah, the cost should go down. So I will later show curves where the runtime goes down. So the failures are still determined by assertions. So initially, when you're in exploration phase, you're trying all these random things and you keep failing all the time. You fail, you try something else, you fail, you try something else. But over time, so you have take certain runtime, but over time you learn that this plan seems to work better. So I will show that curve, it will go down. So another cool thing about this abstraction is that if we don't realize it immediately, is that it's very easy to update a model, right? So you can just add a new model as yet another choice, right? And the optimizer will automatically learn whether it's a good model or not for the given assertions, right? So changing a model is like a very scary software engineering thing right now. Yeah.
So if you add a new model, does the system know that, okay, you have to actually now explore these new paths that you have seen before?
Yes. So it will become yet another plan, and we will just not have any good estimates of that plan yet. But over time, we will try that plan and get a good estimate. And one more cool thing about this is it's robust to data distribution shifts. In theory, we are still working on that. But if your good plan changes, you don't have to redeploy your entire pipeline. Right? The optimizer will relearn that, okay, this plan is working better now, so I should run a different plan. Okay, so this is how the optimizer works. It ingested the monitoring logs from the query executor, and from those logs, it is maintaining probability distributions for runtime of every operator as well as the probability distribution for every plan. And when it ingests a log, it applies a Bayesian update, right? So this is maintained as a beta distribution, and when we see a pass fail, we just update the beta distribution. And similarly for runtime. To pick a sequence of plans, we just do a greedy sampling. So we sample this distribution, we sample this distribution, and then when you're picking a particular position in the sequence, you just see how long it will. So you just try to greedily pick the plan with the least R by P. So R is the runtime, P is the probability of passing. So how long, so when you're minimizing R by P, you try to pick cheap models with high probability of passing. Right? And we just do that using, so there's like a Thompson sampling, multi-arm banded kind of approach in this online learning. So just showing, okay, I'm out of time. So just showing some results. So execution does pipeline parallelism. So we do some pipeline planning, which I did not show. So here, if you just run one plan, then the next plan, then the next plan, then it takes a certain amount of time in Spark and Flink. But in Popper, you can then all the plans, input 1 is going through plan 3, input 2 is currently at plan 1, right? So all the plans are running on the fly. So it can give us 2x speedups. This is the answer to Arka's question. So here we just set up a synthetic benchmark with some known runtimes and probability of passing assertion, but it's not known to the optimizer. So we do that so that we know what is the optimal sequence of plans to run by just minimizing that term. So that optimal is shown as the gray curve here. So the x-axis is the run of this workflow. The y-axis is the time it takes to run the workflow. So notice that even the best plan only has 0.8 probability of passing. This is our operation in between. So that's why it's going up and down. Even the optimal will fail sometimes and roll back. Right? So we see that over time, initially the green curve is the main curve. So initially it has high runtime, but after around 750 runs, it closely follows the optimal. Right? And this can also be seen through the regret curve. So the regret curve becomes horizontal. That means that we are following the optimal runtime. Okay, so basically due to this or not perfectly correlated failures between plans, this approach seems to work well. In the execution, we do pipeline parallel execution, which I didn't really get into the details of. And the optimizer is a multi-arm banded optimizer, which again, we didn't get into too much details. So currently we are working on data distribution shifts. So let's say your pipeline was getting certain ID cards and now it is getting some other ID cards. Can the optimizer quickly learn that I should try this other plan first? We are looking at continuous choices. So currently choices are discrete, but can you say that contrast adjustment of the image is somewhere between 0.7 and 1.3? You figure it out. And the other thing which is most maybe relevant for LLMs is we are trying to push these assertions inside the LLM inference engine in this constrained decoding. So we are trying to integrate Z3 into the decoding pipeline of LLM. So let's say you are asking LLM to generate a JSON with two fields, A and B. So you can say a constraint like A plus B should always be 25. Right? So we are trying to see how to push these assertions inside the LLM engines. Okay, thanks everyone. Yeah.
Any other questions?
Hello, I have one question. Do you have some other use case?
Other than
ID, do we have some other use
Yeah, so the major limitation of Popper is you have to identify these assertions, right? Which is not always trivial, right? So So we have experimented with some question answering use cases. There it seems to work fine. So their assertion there is just the confidence of the QA model should be greater than some threshold. Right? So we have there also it works fine, works well. But that is a big limitation though. You have to say what is the assertion.
Second question, can we think of this as a tool case that can be used by agentic system?
Yeah, that's another good question. So agents is a little bit more tricky. And the problem with agents is that here, the nice thing about this is that your logical pipeline is very well known and your input is flowing through the same logical pipeline, right? And for each of these logical operators, you can define different physical operators. But for agents, what happens is the logical plan itself is figured out on the fly, right? When the user sends the query, then there's a planning stage. They figure out I want to do this, then that. So every pipeline is different, right? You don't get training. You don't get this profile guided optimization opportunity. So we want to look at it, but it sounds like a tough problem.
Thank you.
I heard. Yeah. So when you're trying to measure, so you mentioned that you often want to figure out if the data changes, how fast you're able to react to it in the profiler. So how exactly do you measure that?
Yeah. So for now, that's fine. I showed the regret curves on synthetic workflows. So what we are doing right now is just creating more synthetic workflows and switching the assertion probabilities or switching the runtime of every physical operator, right? And then the optimal changes. So we are doing two kinds of experiments: sudden distribution shift and gradual distribution shift. So you suddenly change the probability to something else, or you gradually move from one probability to another probability. And we want to see how quickly you are able to catch the optimal.
And how do you do predicate pushdown into the LLM engine?
Predicate pushdown,
Sorry, the constraint thing you talked about.
Constraint decoding. So that's more in the exploration phase right now. So, but there is some work already like X grammar and all, which can do context-free grammar pushdown into this. We're just trying to look at how to expand on that. We can talk more.
Okay.
So let's thank Abhilash. So the next talk is by Pankaj Pansari, who is a faculty at Plaksha University. He is interested in improving reasoning abilities of LLMs and speeding up training and inference. He obtained his PhD from Oxford University, where he worked on optimization problems in ML. After PhD, he was a research scientist at Naval Labs in France.
Good afternoon, everyone. This work is about co-scheduling prefills and decodes for better utilization of decode GPUs in a disaggregated LLM serving setting. And I'd like to thank Nipun for valuable discussions on this topic. So first I'll set up the context and some of the background concepts, and then we'll look at, so this is very much a work in progress. We'll look at some of the initial results which we have. So this is like a simplified architecture of the GPU. Okay, so there are these bunch of streaming multiprocessors, and then there's a memory hierarchy. So what's important for us is to know, there's this global memory, which is like the RAM for the GPU. And on top of that, there's the L2 cache, and each SM has these multiple execution units, which are a mix of general purpose cores and tensor cores. Then there are registers and shared memory. And then there's also a L1 cache, which I've not shown here. So for the kind of GPU which I've been working on, H100, you have 132 SMs, and we have 80 GB of global memory, 50 MB of L2 cache, and then there's registers and so on. So now for us, here, what we want is, our aim in this entire kind of work is, or in general, when using the GPUs, how do we keep the SMs as busy as possible? And formally, what we say is that we want any kernel to be in the compute bound regime, where the time it takes to do the flops for that kernel is more than the time it takes to transfer tensors from global memory to the to the registers. And so if the time of compute is more than time of memory transfer, we say it's compute bound, else it's memory bound. So the way it works is that we sort of think about overlapping the memory transfer and the compute times, because like these things get loaded up in chunks. So if I'm transferring weight matrix, I load up in chunk, and it's sort of like this prefetching happening. So because of this, we are able to think about like how do we overlap compute and memory. And we really, if we can be in this regime where the time for compute is more than that, so that's good. And for that, like the numbers are such that for these GPUs which you're looking at, we would have to do a lot of flops for every, let's say, byte of memory which you are getting from the global memory. So it's not easy to be in this regime of compute bound. And we are looking at LLM inference, and the challenges which we'll see is that a lot of times we fall in the memory bound regime. And so how do we kind of deal with that? The LLM inference process is split into a prefill stage and the subsequent decode stages. So in the prefill stage, we take in the prompt which is given by the user and get the first token. And in the meantime, we also store the KV caches, the key values which have been generated in the KV cache. And every subsequent token which is generated, that's called a decode step. And what it does is it takes in the activation of the last generated token, and also it takes in the KV cache and works with that to generate the next token and so on. So this process continues. And every time a decode is happening, new K and Vs are generated. So this KV cache is per layer of the transformer. So let's look at the attention operation in how it differs in the prefill and the decode stages, because prefill and decode, they are computationally very different. They have very different characteristics, and this will probably bring out why it's so. So in the prefill stage, looking at the self-attention operation, we have these query projections of all the different tokens in the prompt and the key projections, and then we kind of get the attention scores. We do a weighted average of the values to get the output. And then whatever keys and values we have, so we kind of don't need to store the queries. The keys and the values which we have, we can store it in the KV cache. And now when the time comes to generate the next token, we take in the sort of the query projection of the last generated token at this layer and load in the keys and the KV cache basically of what we have, append the new key and the value of the last generated token and get this output. So looking at this, what we observe is that in the decode stage, we do have to load the K cache and the V cache, which is a lot of, we'll see like it's a lot of data to transfer from the global memory to the streaming multiprocessor SMs. And basically this indicates that we are kind of loading so much of data, but we are doing very few amount of flops here. And so this is like the key problem, that this makes us go in the memory bound regime. So a lot of data loading, not enough flops doing. Whereas in the prefill, it's a different matter. Say we load the query, the KQV projections, but we are doing a good enough amount of flops that we can bring it to a compute bound regime. So let's look at a simplified like schema of the transformer layer. So we have these KQV projections, then we have the self-attention O projections and FFN. We didn't show like the residual connections element-wise and softmax for simplicity. But these important operations, we can divide it into kind of two, that all the projections, they are sort of the matmulls. And then there's the self-attention, which is a different kind of kernel. And here's how the prefill and the decodes, they differ in their computational characteristics. So for the prefill, both the linear and the self-attention, they usually fall in the compute bound regime. So we usually have enough number of tokens in the prefills, or we can do a bit of batching. It's very easy to kind of be in the compute bound regime for prefill. And so that's good, like that's our aim. So we can easily achieve that. For the decodes, for the linear projections, if we do have a high degree of batching, we can bring it to a compute bound regime, but it does need like a lot of batching. So depending upon the workload and the setup, it might not be possible. The attention part always remains memory bound. There's no way like, I mean, unless we do some KV cache optimizations, but it's like when thinking about decode, like attention is the one which kind of blocks us very much. And so we discuss like the metrics which we'll consider for inference. So we given the query. So here's the user giving in the query to the LLM, and the time it takes to get the first token, that's called time to first token. And so that's the prefill stage, and every subsequent token generation, that the time between that, it's called inter-token latency. So this is the decode part. Now the end-to-end, so let's say here, maybe only 3 tokens are generated or whatever. So from the time when we submit the query to the final token, it's also called end-to-end latency. And these are the metrics, maybe we can stay with that. So these are the metrics which will work with, the kind of workloads which we're considering for LLM serving, those are interactive workloads. So it's not just that we kind of want high throughput. We also, in fact, we care a lot about these latency numbers. Now, what do these numbers look like? That depends upon the workload. Maybe for a chatbot kind of system, we could be a bit lenient with the inter-token latencies. So first of all, maybe it's worth emphasizing that the margin we have for TTFT, so what's called the SLO, service level objective, it's quite generous. So it's usually like sort of not that difficult to satisfy the budget for TTFT or the constraint for TTFT. And the reason for that is that, let's say that you're given a prompt or whatever, like, so let's say we ask a complex question and then it does reasoning and so on. We can tolerate a bit of latency in getting the very first token. Like that's something which we experience, like even when interacting with the models, it's okay. But it's very important that the subsequent decode, that latency is not so much. Because over the lifetime of the whole request, a lot of tokens will be generated. And maybe for things like reasoning models and so on, a lot of tokens are generated, and maybe even for agentic systems. So our focus really is on, like, we would probably have tight target for ITL. The numbers which we are kind of targeting is maybe a few hundred milliseconds for time to first token. But the inter-token latency, we are thinking of like a few tens of milliseconds. So those are strict targets in a way. So the kind of setup which we are looking at like a cluster level LLM deployment, and the kind of serving setup which people have been gravitating towards is the disaggregated serving. Now, before, maybe it's worth saying that before we had disaggregated serving, there was what's called mixed continuous batching. So here we kind of are separating the GPUs by prefills and decodes, but there we would do the prefills and the decodes on the same GPU. And that's great for in terms of throughput utilization generally. But when the latency targets, the decode latency targets, they become tight, it's hard to make that work because there's a lot of interference going on with kind of having prefills and decodes on the same machine. And the challenge, like the key issue is really that what we saw that prefills and decodes, their computational characteristics are very different. So prefills are in the compute bound regime, decodes are in memory bound regime. And so what the prefills are targeting is that, like, we are going to use the codes a lot. And what the decode GPUs are, like the decode steps do is that we are going to use the memory bandwidth a lot. So in a way, they are trying to make like use of different resources, but when in the case of mixed continuous batching, we try to put them together in the same GPU. It does happen that the prefills, they start interfering with the decode latencies. And when the targets are very strict, then in a way, it's hard to kind of make that work. So what people realize is that why don't we put the prefills on their own set of GPUs and the decodes on their own set of GPUs? Because they have sort of like very different computational characteristics. And in this way, probably they will interfere. I mean, they won't interfere, in fact. Well, there's of course like this thing of we do the prefill on these machines, the KV cache gets generated wherever the decodes are going to be scheduled. We would have to transfer the KV cache, but it's in a way kind of with asynchronous KV cache transfer. People have found that it can be made to work. It's not like that terrible. Now, Oh, the specific thing is, yeah, so we allocate some GPUs to the prefills, some to the decodes. And then we also have a sort of set of GPUs which kind of belong to the mixed pool. And here, maybe we can think it's the same thing of continuous mixed batching like Sarthi serve, where prefills and decodes are going on the same GPU. So now the purpose of having this mixed pool is to kind of absorb the load during very high, when there are a lot of requests. So maybe things are piling up on the prefill GPUs or here. So let's say that there's a lot of queue here on the prefill GPUs. So maybe what we can try to bring a GPU from the decode to here and run the prefill on that as well. And then once maybe it eases out the load here, we bring it back to this, like where it was. So we retain the identity. In this kind of setup, it's a bit difficult to kind of switch, let's say, decode GPU to prefill, like because of the KV caches which are resident there. And this system, it generally works quite well for like if the latency targets are sort of quite small, because what you can do is, if let's say the ITL is a few tens of milliseconds, like what we can always get more GPUs in the decodes. And so that way we can speed up like the latency. I mean, we can shorten the latency. Now, so when a model is deployed on the prefill GPUs, like there's sharding which is happening. So the configuration, how do we arrive at how many GPUs to allocate to prefill, decode, what kind of sharding to use, like what would be the degree of tensor parallelism and so on. That is like it's formulated as an optimization problem. So we solve it once, depending on like what is the model which we have, what's the hardware which we have, what's the workload which we're targeting, and what are the SLOs which we have in terms of latency. So we arrive at some like, okay, we need to have these many GPUs and these many pools, and this is how we are going to shard the model. We are going to shard the model there. So this work of disaggregated serving, it took off with these works on in 2024, disserve, splitwise, and PD serve. Now, the problem here is that we are wasting a lot of resources. There's a lot of underutilization happening on the decode GPUs. So prefill GPUs, they being compute bound, they're using it properly, like well. So that's good. But for the decode GPUs, essentially they are making a lot of use of the bandwidth, but they don't make use of all the SMs which are there. So a lot of the SMs in a way sort of are being underutilized. And this is the kind of slack which we are targeting, that yes, we are spinning up so many GPUs on the decode pool to satisfy the latency metric, but like we're wasting so much of resource. Can we reclaim some of those SMs and use them for prefill in such a way that we don't hurt the decode latency by much? So now it no longer remains a pure disaggregated serving, but this is what we are sort of targeting, that can we bring in prefills here by some mechanism which is not the same as the mixed continuous batching as before, which was interfering. We can't adopt that. But is there a way to bring prefills here without hurting the decode latencies by much? And in that way, the utilization of this part increases. And that's what our motivation is. So formally, like our problem statement is that looking at just the decode GPUs, which is like in our experiments, we'll just focus on that. Can we take in a fraction of SMs? And we don't quite know like what's a proper fraction to take in, but can we take in a fraction of the SMs and give it to prefills without degrading the decode latency by much? And there have been, after we had the disaggregated serving work, there have been following works which recognize this sort of waste of compute resource in the decode GPUs and try to put in prefills there. And the sort of, I guess, like the basic philosophy, we kind of are sort of same. We are very similar in that we want to use the compute resources of the decode GPUs in some way by giving it to prefills, but the aims and the mechanisms, they are different. And broadly speaking, I would say that what we want is we want to keep the system more or less like this. So there are GPUs for prefills, then there are GPUs for decodes, but then we take a fraction of these, like each GPU, and try to give it to prefill. Most of the works which kind of are trying to co-locate prefills and decodes, they kind of forego the setup. So what they say is that we take all the GPUs in the system, and like for each of them, let's like have the prefills and the decodes co-located by means of partitioning of the SMs. And in that case, what's going to happen is that the metric which is going to become more important is how well we are utilizing the overall GPUs, like how good is the throughput. So that becomes like the main metric. And the challenge there is that it's very hard to kind of co-schedule prefills on the decode GPUs and satisfy all the prefill workload which you have. So we feel like it's important to kind of keep the prefill GPUs which are there to satisfy the bulk of the prefill request, and then think about repurposing some of the SMs here to give to other prefills. So that is something. Otherwise, what's happening is that if the schemes which kind of have been proposed till now, they do get good utilization out of the whole bunch of GPUs, but they suffer on the decode latency aspect. And depending on the workload, that may be okay. So they go into the few 100-millisecond regime. That may be okay, but when the regime is quite tight, so if we have like a few tens of milliseconds, and that is the reason why we move to disaggregated serving, then it's no longer workable. So in a way, that approach is sort of the scope of what we are targeting is different from the previous work. And also the mechanism is different. So how do we partition the SMs? That's different from, so people have used like other, what's called MPS in GPUs, and that's fine, but it's a bit sort of heavyweight to switch between different partitionings. And we are focusing on green context, which is a bit more lightweight. Well, for batching, for decodes, it's like we do want to batch decodes up to a certain point to get good throughput, but we also hurt the latency. So beyond a point, we don't want to batch the decodes for that. And so what happens in green context is that we allocate some of the SMs, like partition the SMs to belong to one green context and the other, but the rest of the memory hierarchy, it doesn't get partitioned. So we don't have a way to partition really the L2 cache, the global memory, and even the bandwidth. So these are shared resources. And now the challenge is that we are going to run prefill on one, decode on one. There will be contention here. And so how bad is that contention? If it's too bad, then it's going to hurt the decode latencies, yes. And so we ran some micro benchmarks on an H100 GPU by looking at one layer of a transformer with 4K and 8K embedding dimensions with like 32 number of heads and so on. And the context length which we considered is 2K for the decodes. So the first question which arises is that, like, what is the minimum number of SMs we can give to the decodes? And for this, we created two green context, and we swept over the number of SMs which we are putting in that green context on which the decode is running. On the other green context, we don't run anything. And now we see like what is the inter-token latency as we kind of give less and less number of SMs to the decode, and how does it change with the batch size. So what we do see is that let's say till 25% of the SMs, we don't observe anything because it's not compute bound. So we take away the SMs and it doesn't hurt us that much. But beyond a point, the number of SMs which are there, the thread blocks running on that, they are not enough to saturate the memory bandwidth. So this is where it starts hurting us. And we see like the latencies are more for higher batch size and less for low batch size. Now, the next step is that, okay, we can take away some of the SMs from the decodes, but if you're going to run prefills on that, how bad is the contention? How much it degrades? So here on the left, like it's the same plot from before, and oh no, sorry, it's not the same plot. It's in fact So this is the timings for the when we are running the decodes with the prefill running on the other green context. So the prefill also has 2K context length. And because it's not very evident like what the degradation is, so we look at for two batch sizes, 128 and 512, and we see that like the latency increases a bit with running the prefills on the other green context. And this is sort of we are formulating it by like what's the percentage increase in the inter-token latency as we, so these are the different partitions. And here, like maybe you're not able to see the number, so it's like around 6% when we give 10% of the essence to the prefill. When we give 20%, it's like around 10% and so on. Yes, overlap prefills. So now this is quite high, like the 25%, but maybe we don't want to give 40% of the SMs to the prefill. So we have to be mindful of how many prefills are allocated to the prefill. Now, what's the situation like on the prefill side? How does it, so and now the previous experiment that was run by kind of making sure that the prefill is always running on the green context, and then the decodes run, so there's the other green context is never idle. So that's how we kind of get the contention. For this one, how much is prefill hurt by decode running on the other green context? We do it the reverse. So we have the decodes always running on the other green context, and it overlaps fully with the prefill on this one. And what we see is that this is what we do expect, that as we give less number of SMs, in a way, it probably should go down linearly because it's dependent on the SMs to kind of do the flops which it has to do. We do see like it's not properly linear, and I think like there's wave quantization effect going on here. If we had big enough prefill, maybe we would see a smoother linear curve. So what we do observe is that yes, the prefill throughput also does decrease as we. So if we have more batches, so we are batching on the decode side. If we have more batches, then the hit to the prefill throughput is more. Now, what intervention can we do? Can we kind of reduce the amount of contention? And the first idea which we thought of trying out was, can we batch the prefills? So normally, so we have a bunch of requests, and normally we process them serially for the prefills because they are anyways in the compute bound regime for usually. And so we don't get much. In fact, we might be a little hurt by the batching, but here batching serves a different purpose. So let's say if we have 4 prefill requests, then by batching, we are loading every time the wait once over the lifetime of that 4 requests. Whereas if you were trying to do it serially, then over that lifetime, you would be loading it 4 times. So what the decode is seeing is less memory traffic coming from the prefills which are running. And what we observe is that so maybe the solid lines were the ones where we were doing prefills serially. And we see that when we are batching the prefills, the latency decreases to an extent. So that's good news. But this is the case for embedding dimension 4K. For 8K, we don't quite observe. In fact, maybe it's slightly worse off. And the hypothesis here is that it's probably the L2 cache which is hurting because these here, the weight matrices and so on, they are big. So the kind of chunks which are being loaded by the prefills and the decodes in the L2 cache, they are bigger in this case, and 50 MB is not sufficient to work for this. Well, it's actually like there's a get around. It's not so bad because so 8K embedding dimension corresponds to like 70 billion llama parameter model. And usually we don't quite keep like the whole model. We usually shard it. So what's going to happen is that we won't have like that hit. Like it won't be the situation that the L2 cache is not able to accommodate the chunks which the prefill and the decode need at the same time. So although we like haven't done that experiment, but like it can be overcome in a way. So what we are going to like the next steps which we want to do is like properly study like what is the contention going on at the L2 cache level, and knowing that the weight there's a particular usage pattern to the KV cache, and we think that in a way it doesn't need that much of like the need for cache is less. So maybe we can indicate to the GPU by means of CUDA that don't allocate much KV cache to the to the, don't let it persist, the KV cache in the L2. Give more importance to the weight matrices. And then also maybe looking at a final level that what happens, like decode matmul versus let's say prefill attention. What is the contention there? Is it like less and so on? Then we can maybe think of doing some intervention.
Good talk. So, are you aware of this work called Duet Serve from USC? Because they also do, they start with an aggregate, prefill and decode. Then they, wait to see if they have a prediction model, figuring out whether there will be an interference, and then they use green context to actually separate things out.
Right.
So this was out in archive in May this year.
May this year. So I know the name, but I haven't looked at it in detail. I'm again, like it might be, I'll have to look at what is the
Yeah, yeah.
motivation. Like, are they in a way trying to use the
Yes. You will see that,
Yeah,
like
so-
basically the similar kind of thing. So Murali Annavadam is the faculty at USC
Okay.
from his group.
Yeah, is the ITL increase only coming from the decode phase, or is it that prefill is taking more time layer wise? So that like decode, like end to end, it increases.
So
It's like a
the-
pipeline, right? Is the one order of pipeline, the prefill thing,
Yes.
does it take more time? That is that increasing ITL, or is the decode time itself is increasing?
So the ITL is basically like how much is the one decode forward pass in one layer, how
Yeah.
much of time that's taking. And the reason for that increase is basically the prefills which are running on the other SMs. They are making the memory request, which are taking out the bandwidth which the decodes in a way needed. And
Okay.
it's, yeah,
My question is, assume you have a batch of prefill.
yes.
In that time, can we run 2 batches of decode? Or some sort of, is that kind of thing happening, or?
Yeah, so in fact, the decodes are running in a batch. It's a batched decode. So we do batching of decodes. That's
No,
it.
my question is like, you run prefill, like assume in one green context you run the prefill, and from end to end, all the layers put together.
Yes,
And in the another green context, you run decode, right?
right.
Now, do you have one batch in each of that? Or can we have like more than one batch? Like one batch completes and the decode's next batch starts before one prefill completes in that.
No, well, they're not synchronized in a way.
They're not
No, they're not at all synchronized.
Okay.
So they can just like go in parallel.
Okay, let's thank Pankaj again. The last talk of the day, we have Saurabh. He will talk about efficient AI systems work at the infrastructure group at MSR. So he's part of the AI infrastructure group here, and before this, he was at Google.
Okay, thank you, Ashish. I'm going to give an overview of many of the projects here, and it's a very short presentation, so apologies for rushing through all of this. It's going to be very thin on detail. But the idea is that if you find something interesting, please reach out to the respective owner. So for the last few years, we've primarily been working on efficiency of large language model inference. And broadly, you can classify the optimizations there in 2 buckets. First is at the replica level, where there are a few number of GPUs that are working together to service the same request. And optimizations there include things like better kernels for various operations, improving the memory efficiency at a particular GPU, and also better algorithms for scheduling requests at a replica. But at Microsoft scale, we also serve production traffic using thousands of replicas. So here, fleet level inefficiency is also shown quite a bit. And the optimizations here are of the kind where how do you decide which request goes to which replica, how much to provision each data center, what kind of hardware do you want to use, what mix of GPU hardware do you want to use across your data centers, etc. So I'll go through a few of these projects which are hopefully new from the previous academic summit. So the first is a fleet level project called AI Green Fencing. So here the idea is that we have these modular AI data centers, which will be co-located with a renewable power source. And why do we need this? We all know that power demands are going through the roof for these AI workloads. But in order to meet this power demand, upgrading existing grids is very costly. Further, moving power from these existing grids to the data centers is also incurs a lot of losses. So instead, we do have a lot of abundant cheap power available at the renewable power source, which is within a reasonable network latency from Azure data centers. So what we do instead is bring these compute modular data centers to the wind farm, and we serve requests there. So now, when we did a feasibility study with wind energy. The problem with wind energy is that it's not consistent at any particular site. So what you need to do is you have to have multiple sites which give you some amount of complementarity, so you can give some guarantees on consistency of delivery. So then there are multiple problems. First is, as and when the wind energy power changes, how do you decide to turn off the GPUs and how much to downclock the GPU frequencies? And across the sites, you have to decide which request will go to which site based on what the site local controller is telling you, as well as what the latency requirements of that particular request are. So this work, we've done some feasibility study, and you can see the details on an archive paper. We're also planning to do a pilot with an energy vendor. The next fleet level project I'll talk about is Prism LLM. So the idea here is to partition our fleet of replicas into different segments, where one segment will serve requests of short lengths and another will serve requests of larger lengths. Why we need to do this is when we serve requests under a very tight SLO, in order to meet the latency targets, we sometimes have to reduce the batch size to a point where the GPU actually gets underutilized. So, and a key contributor to that underutilization is that the batch consists of requests of different lengths. I'm not going into details of why. Ashwin is a point person on this. He can discuss this in more detail. But once you've decided on segmentation, then there are questions that come up, like what is a short request and what is a long request? How much capacity to give to each of these segments? And when do we want to steal work from maybe another segment? So what we found is if we configure a static policy around this, it can sometimes hurt performance as the traffic shape changes. So Prism LLM has dynamic policies around all of these using the load and utilization metrics that are available in real time. And we see we are able to significantly improve throughput using the same number of replicas with these dynamic policies. I'll move on to some replica level projects now. So Cascade is a sparse attention mechanism, which Aditya has already explained the need of. I'll just talk about the approach here. The primary thing that we do here in order to predict which tokens to attend to is to use this insight called cross-layer similarity. So what we've observed is from one layer to another, the pattern of attention remains somewhat consistent. So we can use that pattern to estimate what are the top K tokens and then apply a top K attention scheme. We've written kernels which are very efficient. And we are able to see on an AIME24 that this approach matches baseline accuracy at 90% sparsity. At the same time, we see a 2x end-to-end speed up on the same benchmark. Sutradhara is a project that optimizes these new upcoming workloads called agentic workloads. So what happens in an agentic workload is that there's an orchestrator. It'll make an LLM call. The LLM call will tell it what tools to run. And then it'll use the tool output and then issue another LLM calls. And this will happen in multiple rounds. So the latency that a user sees is basically a sum of all these serial calls one after another. One of the problems today is that the orchestrator treats the LLM as a black box. So if we can open that up, then we can utilize some parallelism opportunities between the LLM calls and tool calls. Further, because the orchestrator has some idea of what LLM calls it's going to do later, we can pass that information to the LLM, and the LLM will use that to improve its prefix caching policies. So with both these optimizations, we see that we are able to serve the same requests at same end-to-end orchestrated request at about 50% reduced latency. The last project I'll talk about is LLM42. This is a new interesting direction of enabling determinism in LLM inference. So today, if you send a request to an inference stack, if you send the same request twice, you will see different results, even if you set all the randomness parameters to be the same across the two requests. And this is primarily because floating point math is not associative. So reduction operations can change the results based on how which order you do the floating point operations. Now, determinism is important because it's important for reproducibility, and that in turn is important for debugging, and it's also important in domains where you need auditability. So previous approaches to this have primarily relied on writing new kernels, which try to fix this reduction order so that you get consistent results over multiple runs. But LLM42 uses ideas from speculative decoding, where what we know is even the non-deterministic kernels, most of the time they are consistent. Most of the tokens they output will be consistent. So we'll use the non-deterministic kernels to generate a draft set of tokens. And then we'll run a parallel verification step to figure out which tokens are not consistent across multiple runs and discard those and restart our decoding. So with this approach, what we find is, one, we don't need to write new kernels. We can use the existing kernels. And number two, we can somehow, unlike the previous approaches, we can also selectively apply determinism to few kernels, so few requests in the batch as opposed to the entire batch. So again, this is very thin on detail. There are more details around how the verification is also done in a way that we don't have to write new kernels. But yeah, if you want to reach out for more details, Ashish is the right POC. So with that, this is a quick overview. Again, apologies for very thin detail on all these projects. Any questions?
Can you talk a bit more about Sutradhara? So I think you're showing tool use is overlapping with LLM. How is that possible? I didn't-
Yeah. So what happens is a large part of when we run a LLM request, we have a big prompt, and large part of that is tool independent, and some part of it is tool dependent, the output of the previous tools. So what you can do is, as you're running the second LLM call, you can start the prefill, the tool independent prefill, while you're still running the previous tool call. So that is one. The same happens also in the decode part of the previous LLM call. So typically these will output multiple tools to be run. So once they tell you which tool, the first tool that you know, then you can start executing that tool while it's still telling you what are the tools to run. So those are the parallelism opportunities.
I was interested to know about the sparse attention work, and at what granularity are you exploiting the sparsity here? Like, is it any pattern, or are you looking at blocked sparse patterns here?
Yeah, so here this is not blocked. It is a token can attend to any set of tokens before it. But what we exploit is, the problem is when you have multiple heads, multiple queue heads that are sharing the same key head, when you load a key, you want to amortize it across all the queue heads. So for that, we want the same set of top K for all the K heads. So that's the constraint we're using for efficient
Right,
kernels.
right. So that would automatically go into a little bit of a blocked thing, right? Like in some way where you are like the same queue
It's the same K for across multiple
queue.
queues,
Okay.
but it's not like a block of Ks which needs to be loaded at once.
Understood. Thank you.
Thank you, Saurabh. Apologies for going over the time. But I think if there are any other questions, we can follow. Otherwise, we can wrap up. Thank you everyone for attending.